Okay, so let's go through a quick example here. And what we're going to do is start with a problem that we could actually solve, not with this method, just so we can compare it. Let's go through and solve our boundary layer equations for just the classical situation. And let's see how an assumed velocity profile compares with our exact solution, right? The self-similar solution for friction coefficient. So here's the general steps again, right? We start with 1, assume a form for u. 2, we substitute that into the integral form. This up here is our integral form that we just derived. And then that should lead to an ODE in terms of our boundary layer thickness. Right? We want to solve that ODE for boundary layer thickness, and then we can use that boundary layer thickness to compute things we care about, heat transfer coefficient, shear stress. All right. So let's see. To start, here we are. So to start for the problem where we don't have any momentum injected at the surface, right? This is our classical situation. This term is going to go away. And then what do we have? In this right-hand term here, this is allowing us to specify some shear stress at the edge of the boundary layer, which if we have a constant velocity profile, or the velocity is constant in u infinity, there would be no shear at the boundary layer. So this also goes away. So then we end up with, let's see, the following equation. So the simplified version of this that we're actually going to use is going to be d dx, the integral from 0 to delta m of u squared minus u times u infinity dy is equal to what's left on the right-hand side is just minus tau s over rho. Okay, so that's our simplified version of this that we can solve. That's, again, based on just going through and saying there's stuff here that I don't care about, right? I can get rid of it. Let's see, u minus u infinity. I think we're actually neglecting this term as well. Right, so we're just left with momentum change is equal to reaction and shear force. Okay, so then what do we, our step here, step 1, let's assume a functional form for u. So what's a good function that we could use? I mean, you could say, right, u over u infinity is going to be equal to some function of y over delta m. So what's that function going to be? Well, we know that we want the function to do some things, right? We want it to satisfy certain requirements that we have about the problem. What if we chose a linear profile? What if we said our function is, a times y over delta m plus b? It's a linear function. We could do that for sure. The number of things we can enforce about the problem when we have just 2 unknown coefficients is 2, right? We can kind of force it to do 2 things. If you have more coefficients in there, let's say it's a quadratic or a third order polynomial, you can start adding more things that you can force it to do. Like we could force it to have 0 velocity at the boundary, at the 0 velocity at the surface. We could force it to have u infinity velocity at the boundary layer, right? There's these things that we can do that force it to be more like the real solution. So what we're going to do is let's list out some things we want this to accommodate. So our conditions. So our conditions are going to be 1. Let's enforce no slip. So that's going to say u at y equals 0 is equal to 0. The second thing we want to do is let's force the boundary layer velocity to match u infinity, right? So what I'm saying there is u at y equals delta m, right at the edge of the boundary layer, that's equal to u infinity. And so that's 2 things we need our equation to do. There's some other things we might want, like, let's see. We might want the shear stress at the edge of the boundary layer to sort of recover or match the shear at the surface. We want sort of things to be conserved there. So we would say, let's call this shear stress at edge of the boundary layer is recovered. That would mean I'm going to say mu times du dy at y equals delta m is equal to tau at y equals delta m. And those are both equal to 0. So I'm not driving this flow with any shear stress or anything like that. So it has to be 0. Okay, then the last thing that we might want this to do is none of these things actually force us to satisfy the momentum equation. These are all things that tell us something about velocity, or here there's a shear stress, there's a gradient there. None of this is forcing us to satisfy momentum. So let's force the momentum to be the momentum equation to be satisfied, but we can actually only do that at one location with one coefficient. So let's introduce our extra coefficient here, and let's require that our differential x momentum equation is satisfied at the surface. We could pick another location if we wanted to. Let's just do it at the surface. So that gives us this equation: rho times u du dx plus v du dy is equal to minus dp infinity dx plus mu times d squared u dy squared, evaluated this whole thing, this whole equation. I should do this in red so it's clear. So this whole equation has to be evaluated and be true at y equals 0. All right, so in order to accommodate all these things, I need an equation that can do that. So I have 1, 2, 3, 4 requirements. Actually, what this ends up being is you can do kind of one requirement minus the number of coefficients. So what I mean by that is, let's assume our function then is the following: a, some unknown a, plus some unknown b times y over delta m, plus some unknown c times y over delta m, that quantity squared. So let's assume that this is our velocity profile. It's a function of u, right? U and y. All right. So let's do, making that assumption then. What we have to do is then go through and, we're going to make this assumption. We're going to go through, we're going to force this equation to satisfy all those things. And so how would I force this equation to satisfy number 1? I would say my u at y equals 0. So I'd evaluate this whole thing with substituting y equals 0 is equal to u equals 0, right? And then use that to solve for an unknown constant. So we can start by that. So for 1, I'm going to say u over u infinity is equal to 0, right? Is equal to, so for my first equation, I'm going to say a, so it's a plus b times, this is at y equals 0, right? So this is 0 plus c at 0, right? So now I've just, this goes away, so this is saying that a is equal to 0. So I've just forced my velocity equation to satisfy condition 1 if I set a equal to 0. Straightforward, right? Second thing we can do for number 2 is our boundary layer velocity needs to match. So again, we're going to say, so we're going to say u over u infinity is going to equal u infinity over u infinity. Right? That's our second condition. So that's 1. So 1 is going to equal, so I'm going to substitute in, a is already 0, so b. Now I'm at y over delta m, so that becomes delta m over delta m plus c. So I'm delta m over delta m squared. So that's just saying b plus c equals 1. All right, so that's the second thing. So we can't actually resolve that one fully because we have b and c, but we could continue to enforce things here. So we go through for number C, for number 3. So for number 3, we can go through that process and we end up with, what are we trying to do? We're trying to say shear stress. So mu times the derivative of u with respect to y is equal to this tau y at delta m. So that's saying mu times d dy times u infinity b times y over delta m. So we make that substitution in a second, plus c y over delta m squared. That all evaluated at y equals delta m is equal to 0. So if we go through and kind of simplify that out, we end up with b plus 2c is equal to 0. All right, so now I have these two equations. I can solve for b and c. And this is the last thing here we'll do. So let's see, I have b plus c equals 1, b plus 2c equals 0. So to solve for this, I could just subtract the equations. I could say b plus c equals 1 minus b plus 2c is equal to 0, right? Subtract those two equations and I end up with b and b go away. So I end up with minus c is equal to 1, right? So now I have all three of my equations. This actually yields b equals 2. So now I have all three. So now my actual equation is u over u infinity is equal to 2 over y over delta m. So 2 times y over delta m minus y over delta m squared. So this is the velocity profile that enforces at least the first three of those things.